Okay, so today we'll do a few problems on the exponential distribution and the Poisson process. So there are quite a few problems on this problem set, and a lot of them are, especially the first ones, are pretty easy. So I will omit a few of them and just focus on the ones that are a little more challenging. And talk briefly about the exponential distribution and the Poisson process. So, before we start the problems, just a little brief thing about the exponential distribution. If x is distributed as an exponential random variable with parameter lambda, that means that probability that x is less than some number t is 1 minus e to the minus lambda t. Also, the density t is lambda times e to the minus lambda t. And finally, a really useful property that we'll be using over and over and over again is the memoryless property of the exponential distribution, which is unique to this distribution. And it basically says that the probability that our random variable is greater than some value, given that it's already so the probability that x is greater than t1 plus t2, given that it's already greater than t1, is just equal to the probability that x is greater than t2. And this is really useful when we model things. Like if we assume that service times or the lifetime of a machine is exponentially distributed, this is really useful because it basically means that it doesn't matter what's happened in the past in order to predict the future behavior of the random variable. And we can sort of very easily derive this too. This would just be equal to probability that x is greater than t1 plus t2 and x greater than t1 divided by the probability that x is greater than t1. And so this, of course, if x is greater than t1 plus t2, well, obviously x is greater than t1. So we can just write the numerator like this. So we get the following expression, which of course is just equal to e to the minus lambda t2, which is equal to the probability that x is greater than t2. So this is how we get this memoryless property, which is, again, very useful, and you'll see in the problems why. But this is something you definitely should know very well. So now let's start off with problem 4, because the others are just really easy. Okay. Okay, so we have a post office with 2 clerks, and 3 people, A, B, and C, enter simultaneously. A and B go directly to the clerks, while C waits until either A or B leaves before he begins his service. And we want to calculate the probability that A is still in the post office after the other 2 have left. Okay, so we have, let's see. So we have 2 clerks. So So this is actually, I forget how to do this queuing. Anyway, yeah. So this is 2 clerks. And we have 3 people who enter, so A, B, and C. And we want to calculate the probability, so A and B enter service immediately, and C waits. I want to calculate the probability that A is still in the post office when the other 2 have left. Probability A is still being served after B and C have left. So you want this probability here. And there are 3 cases. First is when the service time for each clerk is exactly a non-random number. So let's say that S is the service time. So let's say that S is 10 minutes. And then the second case is when the service times are I with probability 1/3. So S is equal to 1, 2, or 3 with probability 1/3 each. And C when S is exponentially distributed with parameter mu. Okay. So for case A, of course, that probability is 0, right? Because they will both. I mean, I think it's obvious. So let's call this event event E. So in this case, obviously, probability of E is 0, because A will definitely finish, A and B will definitely finish service before C even enters. So it's pretty obvious. Now for part B, the only way that event E can happen is if the service time for both person B and person C is 1/3, right? Of 1, and A has service time 3. That's the only way that event E can happen. So this, of course, is just equal to 1/3 times 1/3 times 1/3, equal to 1/27. It's pretty simple. And now the more interesting case. So when the service times are random and follow an exponential distribution parameter mu, then probability of this event happening is equal to let's actually call let's say that SI is service time. Actually, no. We'll see. You'll see. So first of all, the service time of person A has to be greater than the service time of person B. And then it has to also be greater than the service time of person C. Where? And now, of course, we have this thing happening here. Now, when you have two exponential random variables, so it's actually right here. So if x1 is exponential lambda 1 and x2 is exponential lambda 2, then we know, and they're independent, and x1, x2 are independent, then it's an easy thing to derive that the probability that x1 is less than x2 is just lambda, let's see, is lambda 1 over lambda 2. Lambda 1 over lambda 1 plus lambda 2. Yeah, I think that's right. So in this case, of course, this just means that this probability will be equal to mu over mu plus mu. Let me just make sure. Yeah. And then here, by the memoryless property, this is just equal to the unconditional probability that SA is greater than SC. So again, this is also mu over mu plus mu. So we get an answer of 1/4. Yeah. A little bit bigger? Sure. Yeah, sorry. Any questions on this? And note that if we didn't have the memoryless property, we wouldn't really be able to say that this is equal to this to the unconditional probability. Because now it really doesn't matter how long person A has been in service in order to predict the future, the remaining service time, so to speak. Okay. So let's move on then. Doesn't look very clear. So let's move on to problem 5. So the lifetime of a radio is exponentially distributed with a mean of 10 years. So this means that we have an exponential with 1 lambda equal to 1 over 10. And if Jones buys a 10-year-old radio, what is the probability that it will be working after an additional 10 years? So we want to calculate probability that given that this radio has already been working for 10 years, you want the probability that it will work for an additional 10 years, which means that the lifetime will exceed 20 years. And now by the memoryless property, this is just equal to the probability that t is greater than 10. So this is equal to e to the minus lambda, which in our case is 1 over 10 times 10, which is equal to e to the minus 1. Again, a very straightforward application of the memoryless property there. So let's move on then. So problem 8. In problem 8, we are given what's called the hazard rate function. So the hazard rate function of x, which is just defined as Rx being equal to the density at point x divided by, and now I'm going to use this notation where f bar of x just means 1 minus fx. So this is the hazard rate function, and we want to calculate the expected value of this. So what is expected value of the reciprocal of Rx? So this is pretty easy because we just write the integral. Note that this function can only be positive, right? F is positive, f bar is positive, so this is a positive function. So the integral will be from 0 to infinity, and 1 over Rx is just equal to f bar of x divided by fx. And of course, since we're taking expectation, it's a weighted average, so we have to multiply times fx dx. So we get a nice cancellation here. Now, this is a very useful property when you have a non-negative random variable, but only when you have a non-negative random variable. This integral is equal to the expectation. But so only in this case can we write that this integral is equal to the expectation. So this is a very useful property, and I can actually derive it for you. This is what's called the tail integral formula. So, because we can write this as this double integral here. And now, since everything in this integral, in this double integral is positive, we can exchange the limits. So when we exchange the limits, we want to first integrate with respect to x. So, and y has to be, or rather, let's see what the limits are. So y ranges from x to infinity, x ranges from 0 to infinity. So you don't need to write this. I'm just figuring out the limits. So if we were to integrate first with respect to x, we'd be integrating from 0 to y, and then we'd be integrating y from 0 to infinity. So we would get something like this. Dx fy dy. And now this, of course, is just equal to y times fy dy, which is the expectation of x. So, but note that we can only do this, can only perform this interchange because everything inside here is non-negative, basically. So this is how we get this formula here. It's a very useful formula. So tail integral okay. Now let's move on. Any questions on this? Yeah.
Why would you get expectation of x instead of expectation of y? At the end, you're just integrating.
Yeah, but y is just the variable of integration. I mean, what matters here is...
Call it whatever.
Well, no, it is. I mean, we're saying that x has the distribution, you know, f, right? I mean, yeah, I mean, we're calling this random variable x. Here, this is just the variable with which this could be any letter of the alphabet, right? As long as this matches this is the expectation of x. Okay. So now let's move on. Let's do problem 9. Okay, so now we have two machines. Machine 1 is currently working, and machine 2 will be put in use at a time t from now. If the lifetime of machine I is exponential with rate lambda I, what is the probability that machine 1 is the first machine to fail? So let's say that x1 is the lifetime of machine 1, and x2 is the lifetime of machine 2, and x1 is exponential lambda 1, and x2 is exponential lambda 2. And so machine 1 is currently working, and machine 2 will be put in use at a time t. So we want the probability that machine 1 is the first to fail. And let's call this event A. So now what to do with this, in order to calculate this probability, we just need to condition on what happens to the lifetime of machine 1. So let's see. So given that the lifetime of machine 1 is less than t, what is the probability that it's the first machine to fail? Obviously 1, yeah. So this is just 1. And what is the probability that it's the first to fail given that its lifetime is greater than t? what do we know happens at time t? The other machine is put into use. So this would mean that we get something like this. Right? And now, because of the memoryless property, we know that this is just equal to the unconditional probability of x1 being greater than x2. Because what has happened up till now does not matter in determining the future. And again, since both x1 and x2 are exponential random variables and they're also independent, we know that this will just equal lambda 1 over lambda 1 plus lambda 2. So now we put all of this together, and we get the following. This is just using conditioning. So now we can just write down what the final result is going to be, because we know that this is 1, and this is 1 minus e to the minus lambda 1 times t. So this is what we get in the end. So are there any questions on this? Okay. Yes?
That wouldn't be to calculate that x1 is less than x2?
Is it? Oh, that it's the first. Yeah. Sorry, you're absolutely right. Thanks. Thank you. Yeah. So now let's do problem 11, which is again sort of plays off the same idea. But before we do problem 11, another very useful property is that when we have when x1 and x2 are both exponential and they're independent, and they have parameters lambda 1 and lambda 2, then the minimum of x1 and x2 will also be exponential. Will also be exponential, but with parameter lambda 1 plus lambda 2. And this is also a very useful property. And this is what we'll use in this problem. So let x, y1 to yn. So these are independent exponential random variables. So x is exponential with rate lambda, and all of the yi's are exponential with rate mu. And we want to calculate the probability that x is, or actually before we do that, let's define aj to be the event that the jth smallest of these random variables is one of y1 to yn. Okay. And we want to find the probability that x is greater than the maximum of all of these random variables. Is greater or less? Greater. Okay. So, in order to do this, we have to use some conditioning. So this probability here, say this is equal to p. So p would just be equal to the probability of the intersection of all of the aj events, right? And we know that we can rewrite this now in terms of conditional probabilities. So we can say this is probability of A1 times probability of A1 given A1 and A2. No. A2 given A1 times probability A3 given A1 and A2 all the way to probability AN times probability. Wait, what did I do? Yeah. No, sorry. Stupid. Times. So these are equal because, of course, if you expand any of these conditional probabilities, then you get this consecutive cancellations between the terms, and what you're left with is just probability of the intersection of all the events. Now, make sure I get this right. So now, what is probability of A1? This is the probability that the first smallest is in all the yi variables. So this is the probability that x is greater than the minimum of y1 to yn. Now, we know that this minimum is again an exponential, and each one of these is exponential mu, so this would just be an exponential with parameter n mu. So probability that x is greater than, and we know that x is exponential lambda. So given what we talked about just a little earlier, this would just be n over mu divided by lambda plus n over mu. Now, let's see what one of those intermediate terms would be. So given that the j minus first smallest value is in the, or yeah, is one of the yi random variables, we want to calculate the probability that x is, I get confused with this notation. So that, yeah, so we want to calculate the probability that the jth smallest is still within these y random variables. So this would become, by the memoryless property also, the probability that x is greater than the minimum of, let's say, because I don't want to use the same indices, but all that matters is the number of these random variables. So let's say yi1, yi2, all the way to yi minus j plus 1. Because now we want x to be greater than the minimum of all of these. Because if x were not greater than the minimum, then it would be the jth smallest one, right? So now again, using now the same logic here, actually, this would just be, this is again, this is exponential now with rate n minus j plus 1 times mu. So this is, so this probability would again be kind of along the same line as the first one, n minus j plus 1 times mu. So now we can sort of put everything together. So we know that, yeah, so we can actually write this in a product form. And that's the answer. So are there any questions about this? I mean, what we're using essentially is this property here. And then to derive each one of these probabilities, we're using the memoryless property to equate these two expressions. Okay. So, oh, and we can directly show why this is true also. In the case for n equals 2. So let's verify. Okay. So what is the probability that x is greater than the maximum of y1 and y2? Okay. So now what we end up doing here is that we just condition now on the value of x. So x can range from 0 to infinity. Times so we get the integral probability of that the max of y1 and y2 is less than this number x times lambda times e to the minus lambda x dx. Now, when is the maximum of two numbers smaller than something? Well, when both of the numbers are smaller than the number that we're comparing the maximum to. And since they're independent, actually, I can take it a little slower. This is the probability that y1 is less than x and y2 is less than x times lambda e to the minus lambda x dx. So by independence, we can write this as the product of the two probabilities. Which will give us the following integral. So x1 less than x, so 1 minus e to the minus mu x squared, because they're identically distributed, times lambda e to the minus lambda x dx. And now I don't need really to do the algebra, but just write down the integral, and you get something like this. 2 mu squared over lambda plus mu times lambda plus 2 mu. And let's see if it matches this formula. So this is equal to, say for j is equal to 1, we get 2 times mu over lambda times plus 2 mu. And when j is equal to 2, we get mu over lambda plus mu. So the formula is correct. Okay. So any questions on this one? Yeah.
Get the lambda times
The
top line.
yeah.
Yeah, the lambda.
This one?
Yeah.
Oh, because yeah, I guess I should have. This is just the probability that I'm not going to. This is just fx of x, right? Because x is exponential. It's just the density of x. Any other questions?
The last
Yeah.
1 minus e to the what? Yeah.
Oh, here?
Yeah.
Okay.
Sorry.
1 minus e to the minus mu x. Because, y1 and y2 are both exponential mu, so the CDF of an exponential is 1 minus e to the minus whatever the parameter is times x. Any other questions? Okay, so let's move on to problem 26. Okay. So, let's see. Each entering customer must be served first by server 1, then by server 2, and then by server 3. So we have something like this. This is server 1, this is server 2, and this is server 3. And the amount of time it takes to be served by server I, so let's say service time I is exponential with rate mu I. Okay, and suppose you enter the system when it contains a single customer who is being served by server 3. So we enter, and there is a single customer at server 3. And, okay, we want to calculate some probabilities. So what is the probability that server 3 will still be busy when you move over to server 2? 3 is busy when we go to 2. Well, this just means that we will have finished service at server 1 before the other guy has finished service at service 3. So, and because of the memoryless property, we don't care how long that person has already been being served. So this would just be the probability that S1 is less than S3, which is mu1 over mu1 plus mu3. Now we want the probability that server 3 will be busy when you move over to server 3. So 3 is busy when we go to 3. Well, that's pretty much the same thing, but now not only do we have to finish service at server 1 before this other guy has finished service at service 3, but we will also need to finish service at server 2. And by the memoryless property, this would just be equal to probability S1 less than S3 times probability that S2 is less than S3. And, I mean, it doesn't, I'll just write this down here. Given S3 is greater than S1, which doesn't matter because of the memoryless property. So this is just the probability that S1 is less than S3 times the probability that S2 is less than S3. So you see how things become so simple because of the memoryless property. Because there would be no way you could do this unless the service times were exponential. Otherwise, you would have to somehow condition on how long that other person has already been in service. And then, I mean, it would be a much more complicated thing. So the exponential makes our lives really easy. Because now this is just equal to mu1 over mu1 plus mu3 times mu2 over mu1 plus mu3.
The reason it's not probability of S1 plus S2 is less than S3 is because the exponential too.
So the question is, can you repeat it? Sorry?
Why isn't it the probability that S1 plus S2 is less than S3? Or is that the same?
Yeah, it is the same.
It's the same.
It's the same. So the question was, why isn't it the probability equal to the probability of S1 plus S2 less than S3? And yeah, it is, and I think it is the same. But it's harder to compute, exactly, because S1 plus S2 will have a gamma distribution. And then, you'd have to be conditioning and stuff, and this is just much clearer. But that's a very good point. Yeah?
There isn't a formula for finding the probability that gamma is less than exponential, is there? For finding
The question is there a formula for finding the probability of a gamma being less than an exponential? And not to my knowledge, no. You'd have to kind of brute force do it. I mean, the good thing about the gamma is that, it's the sum of obviously it's the sum of independent exponentials. But there's no real clear-cut way to, it's not as simple as, when you have two exponentials. Okay, so now let's answer the third question. Oops, C, I mean. And so in part C, we want to find the expected amount of time that you spend in the system. Okay. So let's say that Ti is the amount of time spent due to server I. And then T is just T1 plus T2 plus T3. And this is the total amount of time. Okay. So then expected value of T is just equal to the sum of these three expected values. Okay. Now, we directly go to server 1, so this would just be exponential 1 over with the parameter mu, so this would just be 1 over mu1. Similarly with server 2, we never have to wait to go to server 2. But now server 3 is a little different because there is with positive probability that we just calculated, it could be the case that we would arrive at server 3 and we would still have to wait to be served. So this we can say is 1 over mu3. So say that we arrive and, well, no one's there. And this happens with probability 1 minus mu1 times mu2 over 1. Wait, I made a mistake here. Sorry, guys. This is mu2. So mu1 plus mu3 times mu2 plus mu3. So this is the probability that no one's there. And then, well, the server is empty, so we would just spend an average of 1 over mu3. But now say that someone is there. Then we would have to weight an average of 1 over mu2. And then, because we would have to wait, we would have to wait for that guy to finish service. And by memoryless property, doesn't matter how long he's been in service. So we'd have to wait on average the same time for him to finish. And then, of course, we would have to also go into service. So this, let's say that this corresponds to no one in server 3 when we arrive. And this corresponds to someone is actually in service when we arrive. Because there are two things that can happen. And now we can simplify this a little bit. We see that these cancel. So we get 1 over mu1 plus 1 over mu2 plus 1 over mu3 plus 1 over mu3 times this probability. And again, we can only do this because of the memoryless property of the distribution. Otherwise, there's no way we could say that since we've already been waiting so long, well, we'll still wait, the same amount of time, basically. Are there any questions? Okay. I guess we can move on then to the next problem. This is actually a pretty good problem. Like, I would be, I would know how to do this stuff. I wouldn't be surprised if it showed up somewhere. Just knowing how to take advantage of the simple properties of the exponential. Okay. Now we can do problem 39. So, certain scientific theory supposes that mistakes in cell division occur according to a Poisson process. So before we do this, let's say a few things about the Poisson process. So, okay, so let's say that NT is a Poisson process, and it is a counting process. It's a counting process. So it counts events of some kind. And there are three really important properties. The first one is that it has what's called independent increments. So actually, we can do a little picture here as well. So this means that the number of events that happen in disjoint time intervals are independent from one another. If we were to write this mathematically, we would say that for t2 greater than t1, this means independent. So say that this is t1 and this is t2. So the number of events that happen in this time interval, so here we have n t2 minus n t1 events, and here we have n t1 events. So these two things are independent. As long as there's no overlap between the intervals, the number of events that occur are independent. And that's a very important property of Poisson process. Now, another important property is that we have stationary increments. And what this means is that the distribution of the number of events that happen in an interval only depends on the length of the interval itself. It doesn't depend on where the interval begins or ends. All that matters is the length. So this would mean that this random variable here, so the number of events that happen in the interval t1, t2, has the same distribution, this means equals in distribution, to the number of events that would happen in just any interval of length t2 minus t1. So in particular, man, I made them equal here, but say that this is t1. So they'd be equal in distribution to this guy, or for that matter, any other interval anywhere in time of length t2 minus t1. And finally, we can write down explicitly what this distribution is. So n of t is a Poisson random variable with rate, well, if we're assuming that the Poisson process with rate lambda, then the distribution of the number of events up to time t is a Poisson random variable with mean lambda times t. So these are three basic properties that you need to know very well. And they, you use them a lot also in problems, and they come up a lot. Okay. And there are actually a few more properties, which I think are good to have down. So if we say that SI is the arrival time of the nth event, and if we say that XI is the inter-arrival time between the ith and I plus first event, then of course we can write down that xi is just equal to si minus si minus 1. And of course we can, another thing that we can do is say that Sn is just equal to the sum of xi from 1 to n. And because of these three properties, the xi's are IID, so they're independent, identically distributed, exponential random variables with parameter lambda. And that would imply that Sn is a gamma random variable with parameters n and lambda. So, pictorially, this is something like, say this is time t. So you have events occurring. So this is the time of the first event. This is the first interarrival time. Here's the second interarrival time. Here's the time of the second event. And so on and so forth. And all of these are IID exponential random variables with rate lambda. And a final thing, which I think we'll need for one of the problems, is that conditional on the fact that we've had n events occur in a time interval t, the distribution of the arrival times of these events, so this random variable here, is equal in distribution to the order statistics of n independent uniform 0t random variables. Intuitively, what this means is that given that three events have happened, say, from time 0 to time t, well, these events, you can think of them as having occurred uniformly, according to a uniform 0t distribution in the interval 0t. So they're equally likely sort of to have happened anywhere. That's kind of the idea of it. Of course, you have order, because S1 has to be less than S2, obviously. So then you consider the order statistics. But intuitively, all this means is that the arrival times are distributed uniformly from 0 to t. Okay. This is just a long introduction to the Poisson process. So now let's do some of the problems. A certain scientific theory supposes that mistakes in cell division occur according to a Poisson process. So we have this Poisson process here. And mistakes occur with rate 2.5 per year. So lambda is 2.5. And that the same theory assumes that An individual dies when 196 of such mistakes have occurred. So someone dies. Okay. And we want to find the mean lifetime of an individual. Okay. So we assume that these mistakes happen according to a Poisson process. So the time of death will be the time of the 196th arrival of this Poisson process. So this will just be equal to S196, because we're assuming that once you get the 196th mistake, then you die. So let's say that this is t. So then expected value of t is just the expected value of S196. Now S196 we know is gamma with the rate n lambda. So is this visible actually? With 196, sorry. Yeah?
It's a gamma, parentheses what?
Gamma parentheses 196. Let's write down the exact numbers. 196 and 2.5. So so following that, then the expected value of S196 would just be 196 times 2.5. Is that, am I making a mistake? Oh, wait. With the rate 2.5 per year. Oh, per year. I'm sorry, guys. So the rate is 1 over 2.5. It's one of those per year, and it's not 2.5 of those each year. So 2.5 of those per year, but so you get one of them every 1 over 2.5 years. I guess that's how they get the rate. So this would be times 1 over 2.5, and this gives us an answer of 78.4. No, the mean of a gamma is n times lambda. Because also, you know, gamma is a sum of n exponentials. So you're just summing, oh, no. What am I saying? Okay. Because, okay, yeah. Confused. Some books, you know, you always confuse the mean and the rate, which is which. But yeah, of course this is true, and thanks for correcting me. Because if x is exponential, so if y is exponential, then its mean is 1 over lambda. And actually, its variance, let's write this down too, is 1 over lambda squared, right? Yeah. So when y is exponential. So of course, the gamma is the sum of n independent exponentials, so of course it would be 1 over lambda. Thanks a lot. And now, so this is part A. Now for part B, we want the variance of S196. And if you don't remember what the formula is, you can remember that the variance of a sum of independent random variables is equal to the sum of the variances. So this would just be 196 times 1 over 2.5 squared, which gives us an answer of 31.36. Okay, and now I guess we want to approximate some probabilities by using the CLT here. I think you did that in your exam as well, so I don't see much point in. This is just just general sort of you normalize and divide by the standard deviation, see what that comes out to in the normal table. I think so. Parts C through E is just normalize and look at the table. I don't think it's. I think you did it in your exam also, so should be. You should know how to do this by now, I think. So let's move on then to problem 42. So we have a Poisson process again with rate lambda, and okay. So what is the expected value of S4? Well, as we said earlier, and I made a big mistake, it's 4 times 1 over lambda, because S4 is gamma with rate n and lambda, with parameters n and lambda. And more interestingly, let's look at what this expectation is. S4, given that n1 is equal to 2. Okay, so what is this telling us? Saying that at time 2, we've already had 2 events, and we want to find when the 4th event would occur. So this would be S4. Now, of course, the S4 will be after 2, right? So we need to add 2 here. And now here, because, remember, the inter-arrival times are memoryless, are exponential, and therefore memoryless. So it doesn't matter that it doesn't matter when the last arrival before time 2 happened. All that we care about is that time 1, I'm sorry. All that we care about is that at time 1, we have had exactly 2 arrivals. It doesn't matter when they happened. So the next inter-arrival time, or the remaining part of this inter-arrival time, will be again exponential with rate lambda because of the memoryless property. So this will just end up being 2 plus 2 over lambda. And this is 1, I'm sorry. n1 is equal to 2. 1 plus 2 over lambda. And this is because of the memoryless property. Since, so we can write this down, since inter-arrival times are exponential, and let's do the third question. Given n2 is n1 is equal to 3. Now, can someone tell me why this expectation is just equal to the unconditional expectation of n4 minus n2? Remember those three properties? Which property are we using here? So, let's see. So if we know that at time 1 we have, I don't know, 3 events, and now we care about this time interval here, is there any overlap between these intervals? No. So what do we know about non-overlapping intervals? They're independent. The distribution of the number of events in non-overlapping intervals are independent. So that's why this is by independent increments. So this is due to independent increments. And now, what does this equal here? Well, we know that because of stationary increments, this is just equal to, we only care about the length of the interval, so, we only care about an interval of length 2. So this is because of stationary increments. And finally, this uses all the properties, but what is n of 2? It's a Poisson with rate 2 lambda. So this is just 2 times lambda. I think I have time for one last thing. So are there any questions on this? Pretty straightforward, yeah. Yeah.
Ever gonna have a problem where the intervals overlap?
The question is, will you ever have a problem when intervals overlap?
Like if it was like the expectation of n 4 minus n of 2, given that n of 3 is 3.
Yeah, that could happen, right? And that wouldn't be too bad, right? Because if you had something like that, okay, maybe you wouldn't be able to use independent increments directly, but say that you have something like, so expected value n4 minus n2 given n3 is equal to 3. Actually, this might not be so easy. What if we add and subtract n3? Plus so then this would become, now here we can use independent increments, so this would just be lambda. And this would become 3 minus expected value n of 2 given n of 3 is equal to 3. And now this is not, well, see here, this is not easy to compute. I mean, there's no like rough and ready formula. But because, as we said earlier, the inter-arrival times, or the arrival times, are distributed uniformly, this would end up being 2. What's that?
Can you assume that n of 2 is then 2?
No, you can't assume it, but its expectation would turn out to be 2.
Turn out to be 2.
Yeah, I'm pretty sure. Yeah, because, but that's a really good question, because, so this is 3, and we know that 3 events have happened, and they're equally likely to have happened anywhere. So, no, they could have happened anywhere, so here. So this is 1 and 2. And I think, just like very intuitively, you can see why it's expected value, in the expected value sense, it'd probably be equal to 2. But I would have to sit down and think about this a little more.
In theory, you could have had all 3 of them from 2 to 3, right?
Oh yeah.
So
In theory, you could have all of them here, but the distribution is uniform. So, yeah, I'd have to, I'm almost sure that this would just be L plus 3 minus 2. Which would be L plus 1. Almost sure, but I would have to think about this. And I'll send you guys an email about it. Okay, so I guess that concludes our presentation. Thank you.